Let's discuss GATE 2011 question number 44. So let me first write down the question. A spherical steel ball of 12 mm dia is initially at 1000 Kelvin. It is slowly cooled in a surrounding of 300 Kelvin. So surrounding temperature is 300 Kelvin. The heat transfer coefficient between the steel ball and the surroundings is 5 watt per meter square Kelvin. The thermal conductivity of steel, so that's a material property, it is given as 20 watt per meter Kelvin. The temperature difference between the center and the surface of the steel ball is okay. So some parameters are given. It's a question on the lumped heat transfer analysis, and there are options. So option A is large because conduction resistance is far higher than, I'm just writing in a short form, convective resistance is large because conduction resistance is less than convective resistance, and small because conduction resistance, okay, the same thing repeated for small, is greater than convective resistance, and small because conduction resistance is less than convective resistance. So this is all about the question. Okay, so now this is, let's see what is the problem. So you have a spherical steel ball and it is initial temperature is 1000 Kelvin, its diameter is 12 mm, so that means radius is 6 mm, and it's kept in a surrounding where the surrounding temperature is 300. The heat transfer coefficient between this combination steel ball and surroundings is 5 watt per meter square Kelvin, and the thermal conductivity is 20 watt per meter Kelvin. So heat transfer coefficient between the steel ball and the surroundings is given, and the thermal conductivity of the steel ball is given. Okay, now what is asked is the temperature difference. So as it cools, because it's at 1000 Kelvin, and if you keep it in an atmosphere of 300 Kelvin, obviously it will cool. So it's basically like a quenching in air. You have just heated something and kept in air, so it just cools by air, slow cooling. Instead of keeping in the liquid, you have kept in air, where the ambient temperature is 300 Kelvin, 25 degrees Celsius, 27 degrees Celsius. It slowly cools. Now what is asked is, obviously the outer will cool faster than the center core. Okay, so what is asked is the temperature difference between the center and the outer will be smaller or larger based on this conductive and convective. So what dictates this lumped heat transfer analysis? is the Biot number. Okay, and Biot number is defined as HLC by K, where LC is the characteristic length, which is volume of the solid by surface area. So volume of the sphere is 4 by a third pi r cube, and surface area is 4 pi r square. So based on this, we get r by 3 is the LC. So that is nothing but 6 by 3, and that is nothing but 2 mm. Okay, or 0.002 meters. Okay, so now other way of viewing Wyatt number is, Wyatt number can be written as HLC by K, which I can write as 1 by K by 1 by HLC. Well, I can write in this way, right? And 1 by K is nothing but proportional to your, because K dictates your conduction within the material, within the steel ball, what is conductive. Higher the K, higher will be your conductivity, and lesser will be your resistance, conductive resistance. So 1 by K is basically proportional to your conduction resistance. So in the numerator, I can say that 1 by K is proportional to conduction resistance, and 1 by HLC. Higher the heat transfer coefficient, higher will be the convection, and lower will be your convective resistance. So 1 by HLC dictates your, is proportional to your convective resistance. So Biot number can be viewed as a ratio of conduction resistance by convective resistance. Okay, so let's first calculate Biot number because the values are given. So H value is 5, LC we already got 0.02 by 20. So this is 1 by 4, which is 0.0005, so which is very less. In fact, when we study, we say that if the Biot number is less than 0.1, we consider that as a case of lumped analysis. So here it is very less. So what it means, Biot number is small, it means that conduction resistance is less than convective resistance. I mean, conduction resistance is very less than convective resistance, or the other way of saying it is that the center temperature and the outer skin temperature are almost similar, because the conduction resistance is very less and the temperature difference will be very small, or the thermal conductivity is very high. So that's what it means. Biot number very small means compared to the convective resistance, conduction resistance is very low, and the temperature difference between the center and the outer is very small. So the answer for this is D, the small, because conduction resistance. The reason is this, because your temperature difference between the outer and the center will be small only when the conduction is very fast, and that depends on conduction resistance, which the value is low. So the Biot number is something that dictates your lumped heat transfer coefficient. So let's see another question now. Let's discuss GATE 2010 question on fins. So what is given? A fin has 5 mm diameter and 100 mm length. The thermal conductivity of fin material is 400 watt per meter Kelvin. One end of the fin is maintained at 130 degrees Celsius, and its remaining end is exposed to ambient air at 30 degrees Celsius. The convective heat transfer coefficient, which is H, coefficient is 40 watt per meter square Kelvin. The heat loss in watt from the fin is, so there are options given: 0.08, 5, C is 7 and E is 7.8. so let's first see what is the problem. So it's a problem on conduction. So you have a fin, circular fin, so I'm just drawing circular, and dia is 5 mm and length is 100 mm. One end, let's say this end, is maintained at 130 degrees Celsius and the other end is all exposed to the atmosphere, so it can lose heat. Okay, and the atmosphere is 30 degrees Celsius, and another data is the H between the heat transfer coefficient between the surroundings and the steel fin is 40 watt per meter square Kelvin, and the thermal conductivity is also given for the fin material, which is 400 watt per meter Kelvin. So can't say steel, some other material. Okay, so it can, from all the other surfaces, can lose heat. And what is asked is how much is the heat loss. So this is convection from all ends, from all the surfaces, right, except that fixed. It's convection from all the surfaces. So V, and it's a pin fin where the cross section is constant everywhere. Okay, it's a uniform cross sectional fin where the cross section is circular everywhere. So we need to recall the formula. I mean, there are like 3 cases when we derive fin heat loss cases, heat loss derivations when we do. One is we take a long fin, infinite fin. The other is we take a fin where the other end is insulated, and a more general case we take where it's convection from all the surfaces and the fin is finite. So we'll consider that case where it's convection from all the surfaces and the fin is finite. Now, when I say all the surfaces, one end, I'm not considering the end where the temperature is specified. That is always specified. The base temperature is always specified. I'm just talking about the other lateral and the lateral surfaces and the other end surfaces. Okay, and I consider, so this is the case which I consider. The formula for this is a bit lengthy, but then let's do it. So it's hp by k, root hp k, t naught minus t infinity, and tan hyperbolic ml plus h by mk by 1 plus h by mk. Well, you need to, most of the time this case is not given, but this is the first time I'm seeing this case, so you need to just remember this formula where P is the perimeter, which is pi d in this case, and A is the area of cross section, which is pi by 4 d square. M is again parameter that comes from the derivation which we define hp by ka. So in this case it will be h pi d by k pi by 4 d square, so it will become 4h by kd. Okay, so it's now just a matter of substitution and you get the answer. So let's first find out these values. So 4h per kd, so 4h value is given as 40 and k is 400 and the diameter for this is 5 mm, so 0.005. so this value, when I calculate, it comes out closer to 8.944. okay, so that is 8.944. and now if I just substitute everything there, so let's first calculate this root hp by k, or I mean okay, yeah, let's first do it step by step. So hp by k will be root 40, parameter is pi d, that is 5.005, k is 400 into pi by 4 d square 0.005 whole square. So this value, when I calculate, I get 0.070248. so now everything I substitute in this formula. Okay, so I get 0.0740248 for the root hpk. T naught is 130, T infinity is outer ambient temperature 30, and then the big one, the tan hyperbolic. M I have already got 8.944. Length is 100 mm, so it's 0.1 meters. Everything I'm substituting in meters. Plus H is 40 by M is 8.944 into 400, which is K. So this is 1 plus 40 by 8.944 into 400 into again the same thing, tan H 8.944 into 0.1. So this is a gigantic substitution. So when you substitute everything, you'll get that it's close to 5.05 watts. So the closest answer is 5 watts. So only thing, it's all about remembering the formula for this Finn's problem. Most of the time this case is not given. Most of the time either the infinite case or the insulated case is given, and those formulas are very simple. I mean this factor is common in those formulas, only this thing varies depending on the complexity. Okay, this thing is right hand side is 1 for this entire thing is 1 for the basic infinite case. Okay, the answer for this is 5 watts and answer is B. Let's do another problem. Let's do a problem from GATE 2009. So let's write down a coolant fluid at 30 degrees Celsius flows over a heated flat plate, sorry about that. Maintain that constant temperature of 100 degree Celsius. The boundary layer temperature distribution at a given location on the plate may be approximated as T is equal to 30 plus 70 exponential minus y. So this is how it is approximated, where y is in meters is the distance normal to the plate. Okay, and T is in degree Celsius. So if the thermal conductivity of the fluid is 1 watt per meter Kelvin, the local heat transfer coefficient at that location is asked. So the local convective heat transfer coefficient in watt per meter square Kelvin at that location will be. Okay, so we are asked. Okay, so let's first see what is given. So you have a plate which is at 100 degree Celsius uniform, and you have a coolant temperature which is 30 degrees Celsius, and it flows, the coolant fluid flows over the flat plate. So what happens is the layer of the fluid which comes in immediate contact of the plate will obviously attain the temperature of the plate over a period of time. So the steady state temperature distribution would be the fluid which is near the plate will be almost the temperature of the plate 100 degrees Celsius, and as you move away in the normal direction, the temperature will decrease and finally it will reach a steam temperature. So here it will be 100 and the temperature will decrease and finally it will be 30. It will be something like this. It is 100 here as you move away, and somewhere here it will be 30 degrees Celsius. So this will be the temperature profile. Okay, so at this point of time, at this location, what is asked is, so I can say that the heat, okay, so this layer, the layer that comes in contact is at rest. That layer is at rest, no motion because it sticks to the flat plates, the flat plate, and thereby there is only conduction in that layer, because convection is conduction plus fluid motion, but that immediate layer doesn't have any motion, so it's only pure heat transfer that takes place is only by conduction in that immediate layer. The immediate layer is at rest. Okay, so the heat transfer that takes place in that layer is minus Ka. A is this area, I can say area normal, dot dt by dy in that direction. So that is the heat that is getting transferred through that layer. And how much is the heat that is transferred? It is the heat that is converted. Okay, and heat that is converted is HA, the same, this whatever area. So we are just taking a small a, HA. Delta T is the base temperature of the plate minus the far field. So this is TB and this is TB. So when you keep a solid plate, the amount of heat that is converted is HA. The base temperature, the plate is hot, so TB minus T infinity is the amount of heat that is converted, and that is equal to minus Ka dt by dy, and this temperature gradient is at y is equal to 0, because this thing, the conduction occurs only in that immediate layer. Okay, so the entire heat that is converted from the plate will appear as transferring as conductive heat getting to, so the entire heat that is converted from the plate appears as transferred through that immediate layer, or get I just repeat again, the amount of heat that is converted from this flat plate gets transferred through the immediate layer by only means of conduction. That's what this statement says mathematically. So A is whatever area you take, because it's local, you want the local heat transfer coefficient. So A, I'll take only a small, let's say dx into the width. So A anyhow gets cancelled throughout, so H is A if I gets cancelled, so it's minus K dt by dy at y is equal to 0 by H. So let's write down dt by dy. Now T is given as 30 plus 70 e power minus y. So if I find dt by dy, it is 0 plus 70 e power minus y is e power minus y into minus 1. So this is minus 70 e power minus y. Now dt by dy at y is equal to 0 will be minus 70 e power minus 0. So this will be minus 70. Okay, so if I substitute that, it is minus K minus 70 by H. So there is 70 K by H, which is 70 K is the conductivity of the fluid, which is given as, oh my god, K is not given. Yeah, the K is given as 1 and H is given as H is what is needed. So sorry, this has to be TB minus T infinity, because H is what I need. So TB minus T infinity. So this is finally 70 K by TB minus T infinity is the expression for your local heat transfer. So 70 K is 1, TB is 100 minus 30. So that is 70 by 70, which is 1 watt per meter square Kelvin. So this is 1. So this is a straightforward problem, but only thing important, so this is a basic principle in convection. Whenever any fluid is moving through a plate or any solid object, the amount of heat that is converted gets transferred through the immediate layer by conduction. So based on this principle, one can find out the heat transfer coefficient. So the answer is B. Thank you.